Hello, in this video we introduce the concept of equilibrium, how we get to equilibrium, and then how we start to formulate these concepts mathematically. So equilibrium, it's a state in which there's no observable changes as time goes by. Something's happening on the molecular level, but overall the concentrations and the reaction rates are constant. So you achieve chemical equilibrium when you have the rate of the forward and reverse chemical reactions that are equal, and then the concentrations of both reactants and products are constant. So this idea of forward and reverse reactions is one of those things that has been true the whole time you have learned chemistry, but we haven't told you this yet. So we typically write reactions, at least up till this point, in the forward motion, showing that, look, this reaction goes forward, but they can also go backward. There's nothing stopping them, and in fact, technically every reaction can go forward and backwards. It's just that for many of the reactions you've done so far, the reverse reaction is negligible in a way. The rates of both forward and reverse are very low, and the equilibrium position is such that you have pretty much all products, and so you don't need to think about equilibrium when you do that. But now, we're expanding our set of things we can talk about, and we need to start thinking about equilibrium. And so there's a couple different kinds. There's physical equilibrium, and we talked about this when we introduced vapor pressure, right? There's a equilibrium between the evaporation of water and the condensation of water vapor, and the rates of evaporation and condensation are the same. And overall, at equilibrium, the pressure of water is constant, the partial pressure. You can also have chemical equilibrium, where you have the forward reaction. In this case, dinitrogen tetroxide forms two molecules of NO2. It dissociates in a way. And then you have the reverse reaction as well. These NO2 molecules come together and form N2O4. And so you can put this in a flask and just look at it, and especially for this reaction, since both of these are different colors, you can look at it and, see where the equilibrium position is. You'll have both reactants and products at equilibrium. So this is a dynamic process. I think I said this already. The forward and reverse reactions are continually running. It's just the rate is the same, forward and back. And at the moment, we don't care what that rate is. Sure, that's kinetics. How long it takes you to reach equilibrium, that's the realm of kinetics. But for now, when we talk about equilibrium, we don't care how we got there or how long it took us. We just care that we're there, and what does it look like now that we're here. And so here's a cute little plot showing rate of the reaction on the y-axis and time on the x-axis. And so if you start with just straight N2O4, then initially you have a really high rate of the forward reaction, the N2O4, moving to form NO2, and then you initially have none of the reverse reaction, but then as the reaction goes forward, now there's some NO2, so it can start to do the reverse reaction, so on and so forth. Eventually you reach a point where these reaction rates are the same, and then you're at equilibrium, where these rates are the same. We can also rephrase this in terms of concentration. So if we take this same reaction and start with all N2O4, now the y-axis here is concentration, the x-axis is time. And again, this is kind of separate from how long it takes us to get there, but it does show that if you start with N2O4 and initially no NO2, you'll reach some point at which it's at equilibrium, where then after that point, the concentrations are not changing. So we say it has reached equilibrium. Alternately, you could start with NO2. You could start with product, and that works just as well. You have some initial high concentration of NO2 and no of the reactant, none of N2O4. And then your concentrations will change until you hit equilibrium. Okay. Then you can start with a mixture of these reactants and products, and then your concentrations will shift until this reaches equilibrium, and then your concentrations will be the same. Now there is a mathematical relationship between the concentrations of reactants and products based on an equilibrium constant expression, and we'll talk about that in a few slides. So there is a way to figure out what the relationship between these two are at equilibrium. First, though, I got to introduce some math and kind of the formalism by which we do the math when we're talking about equilibria. So say we have the same reaction, and we're going to start with some amount of N2O4. Outside the brackets, this subscript 0 means initially. We have 0.67 molar. And then initially, there's no NO2. So now we tell you at equilibrium, we discovered that the concentration of NO2 is this concentration. So then at equilibrium, what's the concentration of N2O4? And so very typically when we talk about equilibrium, we talk about the math in terms of changes. You know how much you start with. Maybe you know what you have at equilibrium, maybe you don't. But then we calculate the change in going from start to equilibrium, and then we wind up using that to figure out total quantities. So in this case, the change of N2O4 is equal to, well, how much NO2 you produce. So you start with N2O4, you're going to make some NO2, and now you're going to make twice as much nitrogen dioxide as you start with N2O4 that reacts away because of the stoichiometric coefficients here. So if you have, say, the amount of NO2 that you make, well, you have to divide that by 2 to figure out how much N2O4 you reacted away. And so we can do that. Here's how much NO2 we made, and then use the stoichiometry here to find how much N2O4 we had to react in order for this to happen. And then we get a number. So 0.02735 is how much N2O4 reacted away. And so we do this a lot, right? We solve for this change. Once you have the change, then you can take your starting concentration of N2O4, this 0.67 molar initial, and subtract the change from it to make this concentration of N2O4 at equilibrium, 0.643 molar. So again, find what this change is, and then in this case, subtract it from the initial concentration. We know that we're subtracting it because we start with pure N2O4, and at equilibrium, you're going to have some concentration of both. So that means overall, this reaction is going to shift to the right, we say, which means from the start to reaching equilibrium, it's going to take away some of the reactants and form products. So we say it shifts to the right. So then we know that we're going to have to subtract some concentration from the reactant N2O4. All right, transitioning back to equilibrium in general. Here's a table that shows initial concentrations and equilibrium concentrations for this reaction given different starting amounts. And we just did some math on the top line of this table here. So we want to figure out what this ratio is between our reactants and products at equilibrium so that we can then make some sense of this. And all right, well, what if you just take the products divided by the reactants? What do you get? Some number that changes. That's not useful. But if you take the product squared and divide by the reactant, then we get something that is pretty much constant. I mean, the numbers change a little bit because it's experimental data, so there's some noise in here. But NO2 squared divided by N2O4, products divided by reactants, gives us something that's constant, and we call this constant K. Now, this is an uppercase K to denote the equilibrium constant. That's the name we give it. And this is different from the rate law constant, which is lowercase k. So uppercase makes a big difference here. And then the subscript C is to denote that we're doing this in concentration. You can also do this in terms of pressure, but we're not doing that here. We'll do that soon, though. All right. So again, remember, the brackets mean concentration. And all right, if we take the product squared divided by the reactants, we get this equilibrium constant. Now, this is at a given temperature. The equilibrium constant does change with temperature pretty markedly, but we're not there yet. We'll get there. So, all right, you have to flag whatever temperature this is. Hey, here's my constant at 25. Okay. Now, let's generalize this. Unlike the rate law in kinetics, where you couldn't figure the rate law out based on the reaction as written, here with equilibrium constants, you can look right at the reaction and figure out what K is. So here's our generic reaction. A plus B goes to C plus D with some certain stoichiometric coefficients in front. Now, if you have more products or less products, then you just have less or more in the numerator, for example. And then our equilibrium constant is products to the coefficients divided by reactants. So you take the concentration of products, say, and then you, as an exponent, put the stoichiometric coefficient. It might be 1, and that's fine. But sometimes it's 2 or 3 or however many, right? Goes on top. And then on bottom, you do the same thing with the reactants. This is really important. Make sure you know how to do this. We're going to do it for the next month. Okay, this has a name. We call it the law of mass action. I don't really care about the name. I just want you to know how to do equilibrium constants. So here it is again. Now, the magnitude of K tells us something. If our K is much bigger than 1, it tells us that you have many more products than you do reactants. And then we say that this equilibrium lies to the right, in that there's more products than there are reactants, or it favors products. And, in our simplistic reactions we did earlier in chemistry, pretty much all of them we assume lied all the way to the right and, made almost entirely products. And we would just draw that with a single forward arrow. But now, the situation's more complicated and we draw these kind of forward and backwards arrows to denote an equilibrium. On the flip side, if your equilibrium constant K is really small, that means you have way more reactants than products, and we say this equilibrium lies to the left, which implies more reactants than products. Now, if you were to flip this reaction or write it differently, then your K becomes really different, and we'll get to that in a couple slides. But first, take a second to ponder this. These reactions occur at some temperature. Arrange them in order of increasing tendency to go towards completion. So put the least products on the left, the most products on the right, and arrange them based on the equilibrium constant you're given here. Okay, moving on. Now, here's an example. Say you take acetic acid, which is CH3COOH, and then in water, it'll dissociate to form acetate ion, CH3COO, and the hydronium ion, H3O+. Or maybe more simply, you can write this as acetic acid in equilibrium with acetate and H+, but I try to avoid that. So, all right, remember, this is a general thing. You can write the equilibrium constant as products divided by reactants. And since all the coefficients here are 1, we don't have any exponents. Great. But this water is a pure liquid. This is dissolved in water. The concentration of water at, kind of normal temperature is 55 molar. I guarantee you that your acetic acid is going to be nowhere near that concentration. So you'll have big changes in concentration of acetic acid relatively, and whereas that same change in the concentration of water is insignificant. So the concentration of water is pretty much constant, and we just kick it out of the equation. So don't write that in the equation, just ignore it. All right? So don't include solvents in equilibrium constant expressions. Technically, this concentration of water is kind of wrapped up in K, if you want to think of it that way, because it's roughly constant. And failing that, when you do this math in the lab, you want to know concentrations of things. Figuring out your concentration of water is kind of a pain, right? But your concentration of stuff dissolved in the water is pretty straightforward. So omit that. Now, when you have heterogeneous equilibria, when you have solids and liquids and gases, you omit the solids for kind of a similar reason. So say we have calcium carbonate, which is in equilibrium with solid calcium oxide and gaseous carbon dioxide. So you'd think the equilibrium constant would look like this, but, calcium carbonate, calcium oxide are both solids, and it's kind of weird to think of the molarity of a solid in some container where you're capturing the CO2 gas above the solid. How's the concentration there even work, right? Moles per liter, but sure, you could talk about some volume of a solid, but that gets to be a mess, and it doesn't really make much sense. Your overall equilibrium concentration depends on reaction rates, which depends on concentrations, which is going to be really dominated by the concentration of carbon dioxide in the space above these solids. So these concentrations are pretty much constant. The reaction doesn't depend on them, so we omit them just like we omitted the liquid water before. And so now, in this case, our equilibrium constant is just the concentration of CO2. So to review, right, don't put solids in your equilibrium constant expressions. Don't put pure liquids, and then you'll be ready to go. Here's a little picture trying to show this, right? Regardless of the ratio of calcium carbonate and calcium oxide, you have the same pressure of carbon dioxide above these solids. And so therefore, you don't need the solids in your equilibrium constant expression because they don't affect anything, really. Okay, let's talk a little more about the equilibrium constant and how that behaves, because I think this is illustrative for how it's put together and situations you might encounter when dealing with equilibrium constants. So say you have this reaction. It has NO2 in it, but now it's a completely different reaction that we're talking about. The equilibrium constant is going to have the products. NO is squared, so there's a coefficient there. Oxygen's not. In the denominator, you have the reactants. NO2 is squared because there's that coefficient in front of NO2. And okay, here's the equilibrium constant, experimentally determined. Okay. Now, what if you reverse this equation? So now the reactants become products, the products become reactants. Well, if you were to just from scratch rewrite the equilibrium constant, and I'll put a little prime here, so K prime in terms of concentration. Now you have NO2 on top, and then nitric oxide and O2 on the bottom. So really, the relationship between these two equilibrium constants, K and K prime, is just that they're inverse of each other, which if you look at how you write this, hey, that makes sense. If you're putting products on top and reactants on the bottom, if you reverse the two, you're just going to invert your equilibrium constant. And so if you want to find what the K prime is, you just take 1 over 1.55 times 10 to the negative 6th, and there you go. You get the new equilibrium constant K prime. All right, now what if you rebalance the equation and change that around? So let's rephrase this and divide all the stoichiometric coefficients by 2, or in reality, you also multiply them all by 1/2. That's an easier way to think about it for what we're going to do. Now the K prime is nitric oxide, oxygen to the half, and NO2. And so if you look at this, the relationship between K and K prime here is that the K prime is equal to the square root of K. Or, this is the same thing as K to the 1/2. So if you multiply the reaction by 1/2, then you take the original equilibrium constant to the power of 1/2. Which makes sense because coefficients turn into exponents when you form the equilibrium constant. So if you adjust all the coefficients, you take your equilibrium constant to an exponent. That makes some sense too. And this kind of tells us stuff about how equilibrium constants are put together. And we can give you some pedantic little problems of, oh, hey, what's the new equilibrium constant if you do this? And really what we're getting at is, do you understand how equilibrium constants work? All right, so now let's throw a couple examples down here, and then we'll be done. So say we have some container. It's got these concentrations of gases. And now let's calculate what the equilibrium constant is for these following two reactions, just to practice how these go. So let me scoot this up. So now the form of the equilibrium constant is products over reactants. You have to square nitric oxide. You have to square NOBr. All right, so then basically if you want to solve for Kc and you know the concentrations of everything at equilibrium, it's really easy. You just plug the numbers in and solve. So you do that, you get 0.11 molar. Let me pause for a minute and let me talk about units on equilibrium constants. So in this one, right, you have nitric oxide squared and bromine on the top. That's really molar cubed on the top. On the bottom, you have molar squared as units, so that'll cancel out and leave you with molar. You get all kinds of weird units for equilibrium constants. Now, a lot of textbooks just completely omit units on equilibrium constants, and there's a reason why you can justify doing that has to do with activities, and you're making some definition that relates to this other concept that you don't learn until analytical chemistry. So I generally don't care about units on equilibrium constants. Your textbook includes them, and so I try to include them just to be consistent with the book. But I'm okay if you omit them, because a lot of people omit units on their equilibrium constants. It just makes it a lot more simpler, because the units in this case kind of obfuscate what you're trying to look at. Obfuscate, word of the day. All right, so now I'm back to what I'm doing. So let me write the equilibrium constant for this reaction, where everything's been multiplied by 1/2. So you could just write it as is. So here's the form. If you multiplied it by 1/2, put the concentrations in, get a number. Or you could take your original equilibrium concentration, put it to a power of 1/2, which is the same thing as taking the square root. And when you take the square root of a number that's less than 1, it actually gets bigger. Kind of weird how that works. But for now, that's all we have. I'll see you in class.